Archiving started.
Okay. What we're going to do here is run through a problem in MATLAB or Simulink to simulate the performance of a small model rocket powered by an Estes C6 engine. And we'll kind of just walk through the steps of developing this model and implementing it in Simulink. For those in the class that want more practice or more, just another example, I would recommend playing along in Simulink as we go. And of course, you can stop the video at any time to get caught up. So here's our problem to start with. We have a model rocket here. That's a picture of an Estes Alpha, if anybody cares. When it's flying, you have the engine generating the thrust out the back, and the thrust acts in an upwards direction. As it picks up speed, the altitude, we'll say, is positive upward. Also, velocity, we'll say, is positive upward. Drag, aerodynamic drag acts in the opposite direction of the speed. So when the rocket's going up, the drag is going to be a negative value. When the rocket's coming down, the drag will actually be a positive value, because when the rocket's flying this way, the drag is going to act in a positive upward direction. And gravity is another force on the rocket, and that always acts in a downward direction. We have data for the engine in this case, an Estes C6. We have a curve here of thrust as a function of time. That's derived from manufacturer data. People have run these things. You can get data on just about any engine out there. It's pretty easy to come by. And what we did is we put it into a, let me find the right window here. I created a MATLAB script file for an Estes C6 where I have that curve thrust as a function of time. There's that line is the time vector. This is the thrust in newtons. Other information about the engine is a total impulse, which is newton seconds, or the integrated force as a function of time. The weight of the propellant itself is easy to come by. That's 0.01 kilograms. And the engine initial weight, 0.022. And I really should have put the units there, even though they're all kilograms. Comments make a big difference. Having names that actually spell something make a big difference. I just can tell you from personal experience, if you don't document what you're doing carefully, put down the units, put down what you're doing, put down why you're doing it in the comments. When you come back to something like this months or even a year later, you'll be totally lost. So I can run this script file. And if I wanted to do multiple engines, obviously I could have a separate file for each engine, and we could just change engines by rerunning that file. So there's our problem. We want to predict the altitude and velocity as a function of time, and so we can evaluate the performance of this rocket. So sliding down, I've summarized the equations here that we're going to be using. Newton's law is basically F equals ma. Where's my pen? There it is. First one right here. And actually it's the sum of the forces, should have been an S there, is the mass divided by little g times acceleration. Little g here is the conversion from mass to force, really. Because if you look at this equation, the units of here on this side could be newtons, and the units of mass could be kilograms. Acceleration is meters per second squared. The units don't balance, right? So you need g in there where it's, g is force over mass times distance times time squared. And if you're using pounds force and pounds mass, little g is 32.2. If you're using newtons and kilograms, it works out to be 1, because it's basically, you know, 1 newton per 1 kilogram in 1 meter per second squared. So as long as you use meters, seconds, newtons, the units, the numeric value of that is 1, and that's okay. So the forces on the rocket, we kind of drew that picture before. We have thrust, we have drag, we have gravity. The engine thrust is that function we defined. Now, gravity is, of course, function of mass, and as we go, we need to know the mass for this equation. As we burn propellant, that mass is changing all the time. So we need to calculate the engine mass as a function of time. We'll do that by taking the initial mass, which we have, minus the mass of burned propellant. And how much propellant have we burned? Well, if we assume, and let me slide up, this is thrust as a function of time. The amount of thrust that we've burned over at any point in time, or total impulse, you know, if I were to integrate that, you know, at this point I've probably burned, you know, gone through 2/3 of the Newton seconds worth of impulse. So I assume I've gone through 2/3 of the burned mass, or propellant mass. You know, at this point I've gone through 100%. Somewhere over here I've only gone through 10%. So we're going to take this curve, we'll integrate it to find the total impulse, total area under there, and then I can look at it, and as I go, I'll, you know, we integrate as we go, and then by knowing the amount, the Newton seconds we've integrated at any point of time, divided by the total integrated Newton seconds, we'll assume that's the total, the percent of the propellant burned. And from the percent burned and the initial amount available, we can calculate the current available mass. So we say the burned propellant mass is the total mass divided by the fraction of the impulse in Newton seconds already delivered. Aerodynamic drag is the air density times the drag coefficient times frontal area times velocity squared. And just simple by definition, speed is the integration of acceleration. So, you know, we get acceleration from this equation, we integrate that to get speed. Once we have speed, we can integrate that to get altitude. Those are the basic equations. It's pretty straightforward. We could do a lot of math and try to come up with, you know, one equation, or we can just build it from pieces. And for this example, I'm going to build it from pieces for a couple of reasons. One, it's easier, and two, it lets us kind of explore and change things because we can see how this all fits together. So I've started a model. I've got a block here where we're going to determine the drag, and it's not so easy to point to here with the pen. I can't draw on this. We got a block for the engine. Those came from Simulink ports and subsystems there. Somewhere in here is just plain subsystem. Take one of these, drag it onto the model, and then I can open it up and change things in it. Delete that. Oh, come on. I've taken some out ports from sinks, the out. I've put those onto our model already. Here, those are the outputs I'm going to be sending up to Simulink as a matrix of values, so I could manipulate the data in Simulink. I could plot it in Simulink. I can do, or not Simulink, MATLAB, you know, the MATLAB workspace, send it up to MATLAB. I can do what I want. You know, I can plot things, I can do statistics, I can find maximums, minimums, whatever, okay? But let's go, and I've also put some notes here in a comment. My F equals MA divided by G. I also have a note that the rocket empty weight is 0.08 kilograms. I like to put notes all over the model. I've certainly received enough models from other engineers and from academics that it's just the blocks and it's just numbers and it's just connections between the blocks. And you look at it and it's like, what the heck are you doing? You know, I mean, it's just impossible. So I'm a big fan of putting text notes. You know, you can even attach, Simulink lets you attach documents. There's a whole documentation tool, but just simply double-clicking anywhere on the space, you know, you can type notes like that, and it just makes it so easy. I can see there, I look and say, engine thrust is a defined function of time. Engine mass is the initial mass minus burn propellant. Burn propellant is total propellant mass divided by fraction of impulse delivered. So that kind of, when I'm building this model, it leads me to, you know, it leads me down the path of this. These are the things I need to do. And when I'm come along later, trying to understand what is this model doing, I can you know, look at the text, I can look at the blocks, and I can correlate the two. And here we've already got the blocks done, so let's just explore. Clock, this is just outputs the current simulation time. So starting at time 0 is when we get the time input into this table. And this is actually, should have been, rather than the numeric values, what I should have done, and I thought I did clean this up, but I can say thrust time, which is one of my workspace variables. Copy. And C. So I can put in the name of the workspace variable instead of the numeric values. Got too many versions of this model. Okay. C. Control V. Okay, so now it's going to look to the workspace to pick up a variable, which is the time index of the data, and this thrust in newtons as the thrust value. And if I wanted to change engines, I just, you know, load different data into my MATLAB workspace. And okay, so the output of that is the engine thrust in newtons as a function of time. And here I've labeled the signal too. Again, I like to label, I didn't label this clock signal as time. I probably should have, but that's exceedingly obvious. But it's good to know, you know, there's the value, there's the units, and that's an output to the next level of just the thrust, okay? And if I go up to the next level, I see I have this thrust output here, and I'm going to grab on that output and just drag it out into space a little bit. And if I double-click on the signal itself, right on the signal, it creates a signal label, and if I put angle brackets like that, it's going to essentially propagate the signal from below. And because I've labeled the output and I've labeled the signal, and I see that they match, I have some confidence that I didn't miswire things underneath there, which is really easy to do. So that's a straight output. I also wanted to get output the engine weight, okay, in kilograms. Well, to do that, here's my equation. The engine mass is the initial mass minus burnt propellant mass. That's the middle line there. So here's my engine initial mass here in this block, which has, you know, it's a workspace variable again. And I subtract the propellant burned, which is right here. Propellant burned is the total propellant weight, this much, times the fraction burned. So if I burned half of it, that'll be 0.5. So that's the multiplication. And to find that fraction burned, I take the current burned impulse, which is the 1 over S is integration, okay, in MATLAB. And when we get into Laplace transforms in about 2 lectures, that'll be obvious. Well, 2 lectures for the summer. If I reuse this video, you're seeing at the beginning, it'd be more than 2. Okay, I shouldn't do that. So anyhow, this is the integration block. So I take the thrust, I integrate it as a function of time. It tells me the total Newton seconds that I've burned. Divide that by the total Newton seconds that the engine will produce, and I get the fraction burned. Multiply that by the propellant weight, then I've got the propellant burned, and subtract the propellant burned from the initial engine weight, and I get the current engine weight in kilograms, and that's that block. And save. And it should be straightforward to follow because everything's labeled, and I've got the equations, and that really does help. Trust me on that one. Close that. I got another block here, determine drag. Input is airspeed and output is aero drag. That block isn't as done as the previous one. But I do have a couple constants in here. I've got the diameter in meters of the rocket. I've got a C sub d, the drag coefficient. I've got air density in kilograms per meter squared. And I've got the equation that I'm trying to implement here. And I'll move it up here for the fun of it. So this is most of what I need. A couple issues. One, I just picked a constant value of air density, and here's where you have to make trade-offs when you're making models. Obviously, air density changes with outside temperature. It changes with altitude. Do I need to account for that? Or, in this case, since it's just a simple simulation for fun, I'll just use a constant value. If I was doing a real simulation, I might have to put in a table or a calculation of air density as a function of things like temperature and altitude. Same with the coefficient of drag. Here I've just picked a constant value. If this went transonic, then the drag changes in the transonic and supersonic regions, and you'd probably want to do something more complicated. Diameter, I put in a fixed value as opposed to trying to get a workspace variable. If I wanted this to be a more general problem where I was, or general model where I was doing simulations of lots of different rockets of different configurations, I'd probably use workspace variables for things like C sub d and diameter and the rocket empty weight at the top level. And those things would be in another MATLAB file. I have a MATLAB script file that says Estes alpha, and then I'd have another one for a Saturn V, and I'd have another one for something else. So then I'd run a motor file, I'd run the rocket file, and I'd load all the constants I need for that rocket and motor combination. So let's put this together. So we say drag equals air density times drag coefficient times area times velocity squared. So I'm going to be multiplying all this stuff. So I'll go over to my Simulink library browser, go to Math Operations, and I'll get the product block. There. I know because I'm cheating, I'm going to need a couple. So rather than go back to the library browser, I just right-click on that, right-click on the block, and drag, and it makes a copy for me. I'm going to need to get to area. I've got diameter. Area is pi r squared or pi d squared over 4. So I need to square that, and I need to get a pi over 4 term. So math operations, I can pick there's a couple ways to do it. I could just, let's do this two different ways. Let me make this 3 inputs. So if I take my diameter, I can left-click, drag, connect it to there, and if I left-click and drag backwards and pull it up till it touches, and I click there, oops, missed. Again. Okay, I can clean that up. But now what I've done is, I just essentially put the diameter into this product block twice, so that's diameter squared, And I'll label that diameter. And now I need the diameter squared divided by pi over 4. Sources, constant, right there. Drag that in. Double click. Now I'll type in pi divided by 4. Poi. No, this is not Hawaiian food. This is pi divided by 4. I can put in pi as a constant in the MATLAB workspace that's just generally available. I can do a little bit of math in the block, and I can label this pi over 4. And I put that up here, and my output, and I'll send it up to this product for now. This is diameter, or area. Now I need a bunch of connections. I'm going to be multiplying by air density, drag coefficient, area, and velocity squared. So that's 1, 2, 3, 4 things. I'm going to actually put 5 in this for reasons that will become clear in a moment, I hope. And I'm going to delete that line and connect it to the bottom one just to make this neater. Okay. So I got air density. I multiply. Air density comes in here. I've got C sub D. That's multiplied indirectly. And what I did there is, let me undo that. Let me explain one more time. I can drag it a little bit. If I want to route it carefully, I can drag, let go, and I can pick it up, click and drag, and I can, force it to have bends where I want it to have bends, and not where it puts bends all by itself. I have airspeed. If I click on this and I do it connects it automatically for me. I'll save some typing. I tend not to do that just because I don't. I'm going to, since that variable is coming from another level, I'm just going to put my angle brackets on the name. Double click on the line over here, and the name pops up over there. And that way it will inherit the name from further up. My product is arrow drag. I'll just call that drag. The drag, it is getting old. Now I could put units on it if I want. It's not a bad idea. Okay, I got one more thing here, and it's not connected, and obviously I'm up to something, right? Well, that's not air velocity squared, that's just velocity. I need velocity squared. So I will, before I go any further, I will go to Math Operations and Math Function. I'll drag this into here, slide it up, slap it right on top of that line. Open this up. Instead of exponential, I will do magnitude squared. Well, not magnitude squared. I want just squared, right? Square. And this is now v squared. Okay, as I started to say, a funny thing happened on the way to the forum. Let's go back to our picture. I'm going to go back up here. We said that drag, when the velocity is, when the rocket's going up, we have a positive value of drag, right? Our drag is pointing down. When the rocket's coming down, our velocity is negative. The drag has to be positive. So drag has a sign, and that sign happens to be the opposite of the sign of the velocity. And when the problem is when we square the velocity in our equation here, you always get a positive number. doesn't matter if it's going up or going down, I always get a positive number for the drag coming out here, right? And when I put that into my sum of forces, I can subtract to account for the fact that the drag is pointing downward as the rocket goes up, but then, you know, when the rocket's coming back down, it's going to keep thinking that my drag is pulling it down when in fact the drag is retarding the acceleration and, you know, holding it back. So the sign information, the directionality got lost when we squared it. So I have to preserve that somehow, and I think it's in math, sine. So I can take the sine function, S-I-G-N, not sine as in the trigonometric function. I left click and drag it up to there, right? Or another way I can, oops, wrong one. Another way I can do this, I can right click on this line, right click and drag, and I get a branch I create, and click. And now I have preserved that sign information. So my drag coming out of here is going to have, drag will have the same sign as the velocity. Okay? And I misspelled that, but I'm not going to waste time. So that's that block completed. I have a signed value for the drag. The sign is a positive drag means it's pointed up, and a negative drag means it's pointed down, but we can solve that. Let me go up one level. So I have this, I have airspeed. Now I need to put the rest of this model together. So, sum of the forces, right? F equals MAG. What is the force? It's the sum of the forces. So I'm going to have a number of forces. One of the forces is engine thrust. One of the forces is drag. And then the third one is the force of gravity. So I want to go to math and get a sum. Actually, the sum block is this round one, which is kind of weird in this thing. So I'm going to pick up add. So I'll go A for add. Drag this over. Now I'm going to have three things in there. Plus, plus, plus. Now I'm adding three forces. One of them I have directly is the engine thrust. I'll put that in the middle. In newtons, a positive thrust will cause the engine to accelerate upwards, so that's good. I'll connect my drag to this one, and you can see it picked up the name from underneath. Now, oops, here a positive drag is going to, when the velocity is positive, we get a positive number for drag. We need to subtract here, right? We need to subtract that. So I'm going to change that to plus, plus, and make that a minus. And same thing with gravity. Gravity is going to act in a negative direction according to our convention where positive is up. Gravity always acts downward. So I'm going to change the signs to be negative, plus, negative, or subtract, add, subtract. So now I'm subtracting drag, so my positive drag is going to slow the aircraft down because it operates in the opposite, this way it works in the opposite direction of velocity. I need the empty weight of the rocket, sources, constant, and that's 0.08. To make this more universal, I would have made that a workspace variable, empty weight, and I can add the empty weight. Well, right click and drag and just change this to plus plus. can add the empty weight to the weight of the engine at the current time, and I get the total weight. And I'm going to stop doing a lot of labeling, even though I keep telling you it's such a wonderful thing to do. And the other thing is that gives us the mass, okay? I keep saying weight, really that's mass. To get from mass to the force, we need the acceleration of gravity. That's 9.81 in our unit system. So math operations, I'm going to pick up a gain rather than put another source block and a multiply block. I'm just going to use the gain block. .81, and I can stretch this out a little bit so the number is visible and it's easier to follow the model. And I'll connect that there. So now what I have out here is the sum of forces. Of course, to calculate the force, we need the airspeed, obviously, and things, but that's okay. We'll get there. Sum of the forces, I can divide that by the mass. Dun, 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 dun. I'll grab my product block here, and okay, so sum of forces, goes in there, and I need to connect it. I'm going to kind of route this in pieces so it misses things. And let me label this one here, in spite of the fact I said I wouldn't. Mass. And the mass needs to be in the denominator, not the numerator. So I'm going to say, I'm going to change this to be /*. So the top connection is actually in the denominator. The bottom connection is in the numerator. Sure, why not? The output of that is my acceleration. Just drag that out for the moment. If I take acceleration and I go to the continuous menu, I get the integrator with that 1/s in it. I integrate that. I get velocity. Integrate the velocity. I'll just right-click and drag. Integrate the velocity. I get altitude. Okay? And altitude is an output here. I'll just connect that right up. Acceleration. V. I did a control V, not a one. V, and double click on this one, and I get altitude. Move my keyboard up here where it's easier to get to, obviously. Okay, so velocity is one of my outputs, so I can click and drag back and connect that. And I also need velocity or airspeed in my determine drag thing. I'm not very consistent with my names, but at least I can correlate them somehow. And when I double click in here, this should have updated. Yeah, at some point this will update and show the right thing. What else do I need to do? That's most of it. So I have thrust as an output. I'll right-click, route it around and around. Oops. Click and drag. I'm going to rearrange these just a little bit. Move this down here and drag. It's an output. I can go back down underneath that and connect it there. I'll grab this segment, pull it down, and kind of neaten this stuff up a bit. You can make a career out of aligning blocks and making it perfect, you know. At some point you got to cut the losses and ship the model. That's a relatively complete model. One thing is, when do you stop, right? Do you stop? Do you just let it run forever? I mean, if I let it run forever, it'll go up, it'll come down, and it'll keep going below the surface. That's not, that's a little bizarre. I can say, well, I'll stop when the altitude reaches the maximum. If I only care about the maximum altitude, I'll look at the sign of the velocity. When the sign of the velocity, when the velocity goes negative, I could stop it then. Or I could put in a fixed time up here in my simulation parameters. I can say I'll stop after, 10 seconds or 20 seconds. What I'm going to do is I'm going to make the simulation stop when it comes back to the ground, so I can see the entire flight profile. A real Estes alpha would pop a parachute after a number of seconds, and that might be a good way to stop it, a good reason to pick. If I had say a 5-second delay on the engine between the parachute popping, I could make that 5 seconds, and then I could see, I'd have to make it 5 seconds plus the engine thrust time, I think. But I could, see at what altitude the parachute would deploy. There's a lot of ways to do this, but what we're going to do is run it right back down to the ground, because it's more fun to crash a rocket than to pop the parachute, right? So I'm going to click on Logic and Bit Operators. And I'm going to compare to a constant, drag this in here, and what I'm going to say is if the altitude is less than minus 0.01, so my altitude has gone negative, okay, that gives me a little bit of crumple zone for my nose going, right? If it's gone, the altitude's gone negative, we've obviously hit the ground. Drag this back to altitude, and I need the, where is that one? Model-wide utilities? No. Yeah, I forgot, there's a stop block, and I've forgotten where it is. Discrete logic and bit operators, I was just there. It's not there. Sometimes you just kind of, you forget, and there's not an obvious place for it. Signal attributes, signal routing, syncs. Oh, it's a sync. Okay. Because it just accepts data and dead ends it. Okay. So there's a stop. So when this compare to constant becomes true, the simulation will just stop. Now here I have all the data going to the workspace. Oops, this acceleration isn't connected. That goes right there. Now they're all connected. But sometimes I might want to just see what's happening right here in the model. I've got syncs open. I can put a scope. I can put scope there. I can connect it back to the altitude. If I double click on this, one of the things I like to do is click on Properties, History, and uncheck Limit Data Points. Properties is the second little icon. So if I run this simulation, it's going to be unhappy because we've got a data problem. Yes, the stop simulation wants a, what kind of data does it want? That's to uint. The input data type must be either double or Boolean. Okay. So if I double click on compare to constant, we have this output data type option. The default is apparently uint8. If I change that to Boolean, that's a data type that the simulation can, stop simulation block will accept. Try that. And, it's happy. Amazing. If I double click on the scope, drag it up here, click on that block. Except I stopped at 10 seconds because I still have 10 seconds in my simulation parameters, so I can just make this 100. I could make it INF for infinite, then it would just run but, you know, let's not get carried away. So there it is, the altitude profile, 190 meters or so. It took about 13.5 seconds from the time we triggered this model to the time it impacted the ground. And let's, rather than spend a lot of time dragging and attaching scopes, I have a version already done like that. Run this one, and let's see if we get the same result. Yeah, same result. So I obviously did the same thing twice in a row. That's the altitude. I can look at drag, and I can see that the drag, again, when the, well, let's pop up velocity here. Velocity, okay. So the velocity is increasing, the rocket's accelerating for the first about 1.5 seconds, then the velocity is decreasing but still positive until you get to about a little after 6 seconds, and that would be at the peak altitude. And if I go back to my altitude 1 distance, yeah, you know, this is where the altitude peaked, and now it's coming back down. Pick up drag, and you can see that the drag went negative just after 6 seconds at the point in time where the velocity went negative. So that's, you know, that part worked. I can also look at my mass as a function of time, and you can see, you know, it starts out up here at 0.102 and comes down as the propellant was burned, and then it's constant. And I can look at thrust right there, make that bigger, and again you can see that this was essentially the same curve for the engine that we saw before, and it runs for, you know, about 1 3/4 seconds, and it's done. So that's a complete simulation. Things are labeled, you know, so we can play with it and move things. By using these angle brackets, I propagate variables, and I can see at this level that the signal coming out of the determined drag block is the arrow drag, and that matches the label on that. You know, because I've labeled these out ports here. The default is just, you know, out, and then you can relabel these with whatever name you want. Anything else exciting that's going on here? But having these labels on everything, you know, I can match the label on the signal with the label on the subsystem block. Going back into airspeed here, I have airspeed is my signal name. I have velocity as the auto-propagated name, and you know, that just gives me a little more confidence that I didn't make a mistake. It's one more way to kind of double check the results. You know, if I'm looking at a model and I see a mismatch between the label on a port and the label on the signal, oh, I found a bug, and it's very easy, and it really pays off. So I think that's all we really need to cover. I like this example. I hope you enjoyed it and played along, and talk to you next time. Oops. Find the right window here. That's the window I want, and we can stop the archive.